All right, so I'm probably the outlier in this group. And yesterday I actually panicked and went to coach Ravi and said, what do I present? I had some presentation earlier, which was a focused approach on recovery of networks. But anyway, when I panicked and went to Ravi, he said, didn't you know your purpose always was to mesmerize the audience with your brilliant sense of humor? So what I'll try to do right now is provide some comic relief. Hopefully also as we go through this, this is a little bit more on the application side of things. So hopefully there is a lot that some of us who work in areas like climate, water, energy, infrastructures, we can use from some of the interesting things that you guys do. I only have a very rough idea of what you guys do, but I can see that there are ways in which we can use this. So hopefully some of this will motivate that discussion a little bit. And you will see that my talk relates neither to games, nor to epidemics, nor to behavior. So we'll see where it goes. By the way, in terms of managing the unavoidable, I've been talking with some of you. Climate means different things to many of us. There is mitigation, where you're trying to, what is called, avoid the unmanageable. Beyond the point, there is only so much you can do. Then there are certain things that will happen, even if we were to stop all greenhouse gas emissions today, which is not likely. And that is what we call adaptation, which is managing the unavoidable. Most of my talk will focus on that aspect of climate. I'm sorry? At least the and is there, yes. So I'll tell you why that and also comes a little bit. All right, so first of all, a little bit about climate. This is not one of our slides. This comes from multiple national labs, especially Oak Ridge National Lab, where I used to be earlier. So this is sort of one of the many smoking guns, if you will, when we talk about, yes, climate change and so on. What you're looking here, this is anomalies. Anomalies have a very specific meaning in climate. It just means departure from some long-term average. So it's not what you think as a statistical anomaly. It has a very specific meaning. And this is departure of temperature from long-term average. The black line here, that's observations. The pink line here, that's all forcings, meaning human-induced greenhouse gases and natural greenhouse gases. The blue line here, that's artificially from the model you have removed human-induced greenhouse gases. And this range of variability, that's the range of variability from models. So if you see from around here till about 1920s, even 1940s, all of these simulations more or less followed the observations. There's, of course, a lot of variability here, but more or less. And natural and all forcing sort of followed each other. Around 1940s, and as all of you know, many important things happened around that time, these two begin to diverge. So without human emissions, what you're saying is we'd be living in a slightly cooling environment right now. Slightly global cooling environment. However, what this shows is we are warming, and indeed observations follows that. So this is one of the smoking guns in terms of climate. You had a question? Observations. Simulations. One is with human and non-human natural forcings, another is just with human forcings. If you're Donald Trump, you'd not be in this conference. But yes, you'd question all this thing. You'd question models. Do they agree with observations? You'd say that, what do we know? You don't know what you're talking about. Right. No. So each of these things, as you know, climate is a complex system which goes beyond some of the complexity, that we have been seeing here. There are valid uncertainties which needs to be, areas of active research. The problem that happens sometimes with climate, not everywhere, but sometimes is there are sort of non-valid manufactured uncertainties where a lot of time goes. And that's what we want to avoid, which is not to say that we should not spend time in uncertainties. In fact, I'll talk about some of them. I'll show you where some of the major uncertainties are. All right, so here we are talking about, this comes from IPCC, Intergovernmental Panel on Climate Change, but it also, I mean, we have seen variants elsewhere, talks about disaster and hazards. So here is a weather and climate event. If you're from the US, think about Hurricane Katrina. If you're from India, think about Chennai floods. If you are from somewhere else, please make up something because I don't know. But let's say Chennai floods and Hurricane Katrina, right? So that's the weather and climate hazard or event, probability of hazard. And then we have vulnerability, which is probability of damage given hazard. In the context of Katrina, this is the fact that that levee broke. Katrina came, that was the hurricane, and almost went away, seemed to go away, but then that levee broke, and that's what caused the damage. In terms of exposure, that's the fact that people in New Orleans were vulnerable to start with. There was ghettoization, people were living below sea level rise, and so on. And you can make, I mean, analogies with Chennai flood. So there are these three things: the threat, the vulnerability, and the exposure. The hazards in an insurance world, for example, and some other words, these were thought to be, these are still sometimes called acts of God. Right? Whether she exists or not is another question, but just these are called acts of God. However, be that as it may, definitely a disaster is not a hazard. Disaster happens when these extremes act together with vulnerability and exposure, and that definitely is inaction of man. Just 1 second. In fact, even this act of God, now with global warming and the effects of that on climate extremes, one could question, is that even just an act of God? Yes. Yes, I'll show you some examples of that. So there are two things here. One is let's say, heavy rainfall event, or hurricane, if you will. Something may happen to the intensity, duration, and frequency of those events, statistically speaking. So whatever we saw on an average over the last 30 years may not be the same over the next 30 years. So that's one thing that we look at. Climate, usually we're looking at averages of weather. And the other thing is exactly what you said. There is a gradual rise in, for example, sea level rise in marine ecosystems. So we'll talk a little bit about some of those things. Not all of those, but yes. But this construct is more designed for discrete events, this particular construct. So anyway, so here we are, I mean, we can even question whether for natural hazards even this is so true. I mean, we have, action of man, but definitely when it comes to vulnerability exposure, it's something that we can do. So let's talk about this part a little bit, extremes under climate variability and climate change. So I'll talk a little bit, of course, I mean, I'll just show some examples of our papers simply because I know them best, but there is a whole line of work in this area. This was a paper that we published in PNAS in 2009, which talked about heat waves, which said that trends in heat waves are more than what we thought, but so are the uncertainties and geographical variability. These uncertainties are at high resolutions, which was higher. The overall trends was also higher. So in terms of cold snaps, though, what we saw is an interesting thing. What we saw is that cold snaps will persist. This was a paper in GRL, which got some attention, was 2011. I mean, this was 2011. This said that cold snaps will persist in the sense that the frequencies will decrease, but the ones that do happen will be as intense and as long-lasting as the ones that we happen right now. So basically what we are saying, and this was not this paper, but in a 2014 paper in Scientific Reports, what we said is, so if this is an approximation of climate as it's now, this is temperature, let's say, this would be heat waves, and this would be, let's say, cold snaps. So, I mean, just warming would mean that you are moving this at some point. But what we are also saying is that, and just increase in variance would be something like this. What we are saying is that the variance increases actually somewhat more here but also here, and there is this shift. So there is warming, variance increases more here because of certain natural, what we usually think of as natural variability, which are exacerbated a bit because of the warming. And of course, in heat waves too. So it's not a symmetric, direct change in terms of the extremes. So that was an interesting finding. Boston has been experiencing, as you might know. So what we are saying in the future is that the frequencies of these will decrease, but you'll have those. And this is interesting because this says that you cannot relax your adaptation to cold snaps just because you're thinking of global warming. What this says is, this is about rainfall extremes. What this is saying that we have been observing over time that the more extreme rainfall, they have been growing more intense and longer lasting. And what used to be a 40-year extreme, I think most of you know what a T-year extreme is, 100-year extreme. This is just an extreme that can happen on an average, stochastically speaking, once every 100 years, means the chance of that happening in the very next year. If it has already happened this year, the chance of that event happening in the very next year is 0, right? No, you're not sleeping. So it's 1 over 100 still, right? So that's a 100-year extreme, T-year extreme. And that's what we are seeing is that what used to be 40-year extremes in 1930s is already 30-year extremes and could well become 5-year extremes by 2100 for the business as usual scenario. There's an interesting physics behind this. So if you have an atmospheric column, and if you are saying that, if the T goes up, there is a mechanism called Clausius-Clapeyron, which sort of follows from Dalton's law of partial pressure. You can look this up if you want, which basically says that the amount of water vapor that can evaporate into this atmospheric column increases. A very rough way to think, meteorologists will call this bad physics, but a rough way to think is that the water holding capacity of this atmospheric column increases. What that means is, on an average, more of that water can fall down as rain when conditions are right. So you'll not observe this relation everywhere because conditions have to be right for it to rain, like aerosols, this, that, all kinds of things. But on an average, you'll see this relation, and that's what we're seeing. So although there is a lot of uncertainty, by the way, in rainfall itself and in hydrology, rainfall extremes, that pattern is a little bit more discernible. And I'll show you some of the uncertainties we see in hydrology, by the way. So anyway, and then these can hopefully give some sense of plausible insights. This, by the way, is just one scenario from one climate model, one initial condition run, and together with population. So this includes changes in population, changes in demand and supply, and here is what you're saying in the US, where some of the stresses might be. We cannot look at just one scenario, and we have to correct for various errors here, but this is just to give you an idea. Some other kinds of insights. So this is in terms of water energy nexus. This was some work we did for ARPA-E, US Department of Energy. And when you take into account the fact that climate models are A, chaotic, and B, there is a lot of stochastic uncertainty, together with all that, it's a very hard problem for some of these things like hydrology. But what we do is we look at a huge class of ensembles of these model runs, and then we try to see what this is telling us. So at least here, this is saying that, look, most of these ensembles are going towards scarcer and warmer. Scarcer water is something that has impact on energy, of course, energy production. Warmer water is also important in terms of efficiency of energy production and in terms of what happens to discharge ecosystems, because there are laws about how much warmer water you can discharge. So that's some of the things that you observe. Now, I'll remember this a little bit. I'll come back to another thing which is similar. We spoke about marine ecology. This was a paper that came up last year. We published this in Nature. This talks about how climate change will intensify upwelling, coastal upwelling in this process where near the coast you have water moving like this, which is useful for species, ecosystems, fisheries, because nutrient-rich water comes up, and that's what they use for survival. However, this process, if it is too fast, can get into an overdrive and can give you dead zones like Gulf of Mexico. So it's important for ecologists to try and understand this. And what we saw is that there are two things. One is that there will be an intensification of upwelling, and two is there is a spatial homogenization. So some of the variability is actually decreasing, over latitudes, which was very interesting finding. So when we come to all these problems, whether it's the science of climate, the extremes, whether it's impacts, we have this issue. So, we have been, some of us and others in climate have been dealing with large data set for a while, till I think, Ravi came up with this new cool thing called big data, right? Not one of you guys coined the term. And we are happy to use that, fine. Yes, we are dealing with big data. The problem also is that we have this thing about, we're really interested often in the small data. So we're interested in the 100-year extremes. We're interested in what causes abrupt change. We're interested in things like teleconnections, correlations, and so on. So some of the challenges, so this, by the way, was, this is not, our work, this is some perspective paper in Science which talked about, this was a whole big data issue in Science which talked about climate, and here's how this data set is going to increase from observations, remote sensing, etc. The challenges, as we see this in these data areas, first of all, it's geographical data. So, there are space-time things. Some of you may know, if you are from fields related to geography, you have heard about the first law of geography, which is basically that things that are close to each other are usually related more to each other than things that are further off, basically just autocorrelation. And that you have in space and time. However, in these kind of areas, we have other things. We have teleconnections, El Nino, which is a phenomena happening in the eastern part of the Pacific, impacts weather patterns all over the world, especially in tropics and subtropics. And this has got nothing to do with climate change. This is just usual climate variability, interannual variability. So that's one of the things that we have. In addition to spatial correlation, we have these long-term correlations. The other thing is we have long memory processes over time. So if you have read your Bible well, you'll remember things like 7-year floods and 7-year droughts. And there's a reason for that. These are just long memory processes. Droughts and floods, once they get into a certain state, they sort of tend to stay in the state. And maybe the Hearst phenomena over that region of the world at that time was such that 7 years made sense, right? So those kind of things. Now, then we have chaos and sensitivity to initial conditions. There's a reason why I'm sort of differentiating between these two. As you know much better than me, chaos is extreme sensitivity to initial conditions. Here we have something else also, which I'll talk about eventually. We have randomness, all the way from Gaussian distributions to random walk to what is called 1/f noise, right? And then we have nonlinear dependence. And of course, we are very interested in extremes. Extremes including abrupt change. So extremes in the differences, if you will. And we are interested in multivariate extremes, spatiotemporal extremes. So that's where some of the challenges come in here. That's where some of the uncertainties come in. And that's where we need a lot of help from computer scientists, physicists, and mathematicians in general, including from all of you. And that's where also I happen to be working with some computer scientists. So here is one example. This is hydrology. This is delta P minus E, precipitation minus evaporation. And these are 5-year averages, 30-year differences. Current conditions, 30-year hence. 5-year averages. Why 5-year averages? Climate is an average weather quantity. Even 5-year is less, but 30 years, we just tried that. P minus E, precipitation, total rainfall falling down, evaporation, total water getting up. Mass balance sense, total water in the land or vegetation, terrestrial biosphere, total water there. That's all that this is, changes in that. This is change in, this is change in that, delta P minus E. Now, what are these things? Along the column, these are 3 different US models. By the way, the climate modeling group, there are about 25 to 30 modeling groups across the world, and each of them produce one set of simulations. By set of simulations, I mean according to different greenhouse gas emissions scenarios in the future. We don't know exactly what that will be, so there are scenarios and different initial conditions. And this process is coordinated by the IPCC, and I mean, one of the data warehouses are US Department of Energy's Lawrence Livermore National Lab. There are others. So all of these are stored somewhere. So from that data set, what I have is 3 models. Model 1, this column, model 2, this column, model 3 here. Ignore the ones on the margins for now. Model 1, model 2, model 3. And here, along the rows, I have different initial conditions. Now, in general, if you look at temperature, variability, that look much better. This one doesn't look that well. So different models, go back to your Lorentz equation, change the parameters of those models. Lorentz equations, by the way, came from Ed Lawrence, who was a meteorologist, so it's not that far away as a field. Change the parameters of those models slightly, but still so that they are within chaotic regime. And the other thing is initial conditions, so change your initial condition. Typically, you would expect that at least there would be a cluster. Each model would behave in a similar way with some things in the initial conditions. But there are things like these, and this is one of the harder examples, purposely selected. Not everything is that bad. But in hydrology, things like these, where these initial conditions matter so much that it's hard to even distinguish between what is an initial condition and what is a model. Yes, you had a question. Yeah, so there is a bit of, yes, so there is a little bit of debate on that. First of all, it's a little bit different predicting weather, yes, go ahead. Okay. So the first question was, are these climate models good at predicting anything we care about in the short term or interannual terms, such as these polar vortices? The second question was, do we need to look at this level of detail, especially for mitigation, or do we look at simple physics and see what we can do from there, right? Because these, at this level of detail, things are bound to be, not exactly the same. And here, it's one example where it's relatively extreme, but this was not just chosen out of the hat. This example was needed for this, for a problem in water energy, which is given to us by an agency. Anyway, so to get back to your question, first of all, there's a little bit of, so I'd like to take the on the polar vortex issue, simply because that's more of a, that's like predicting monsoon next year, which is important. It's seasonal to interannual predictions. Different. That has a whole, that is a different topic. The answer is not no, the answer is yes, there were some, but that's a whole different topic. Climate, remember, is an average quantity, at least 5-10-year average, usually 30-year average. There's nothing, significant about this 30, but that's usually what you consider because many of the natural variability things die off at that scale. So that's one thing. The other thing, though, I wouldn't quite agree with that assessment, and I don't think most of our community would agree in terms of we have to only look at simple physics and ignore all this. And the reason is, we should look at simple physics, by the way, and we do. Integrated assessment models look at that. The point is that those simple physics won't give you any assessments of extremes. Now, if I want to plan for an urban area, and urban areas both contribute a lot in terms of climate, and they're impacted the most, I don't have any guideline. Now, you would say, is this guideline any helpful? Any use? I'll come to that in a minute. And again, this is one of the harshest case. If you look at heat waves, we have better guidelines. But at least we have something. These are plausible futures, right? These are things that are physically consistent, at least. And can we use them for planning? So this is like saying that, if I do a projection of how much traffic I'll expect in my bridge, right? Do I plan for mean traffic? Usually not. Then I'll be repairing this bridge every, peak hour. Do I plan for the peak daily traffic? Usually not, because what happens when there is a big ball game or cricket game or whatever, what have you? right? So you usually try to prepare for something which is one of the harshest conditions, but then there are economic considerations that step in, that, okay, you don't make your dam so high that you have to put all your resources there at the expense of something else, or your bridge, build your bridge of titanium or whatever it is, right? That you cannot do. So there is always this economic consideration. But we don't design for averages. We design for something that's high, and then we consider economic considerations. Here, if you look at the mean, by the way, look at the mean of all of these 6, that's this one. That is basically saying there's no change. So the idea would be to use these to say that, look, these give us bounds, these give us plausible futures. There are areas where we are just predicting a few seconds or few days in advance, and we can make a lot of money. Here we are predicting years in advance. We have to be cognizant of these uncertainties, but we have to deal with them. We cannot say that this is an average, and hence we do nothing. Or even if it says do this, we have to be aware of these plausible futures, different things that can happen, and then based on economic conditions, we do what is needed. So we have to be careful that there could be flood years, there could be situations in some places where we get more and more floods, in some other places where we get more and more droughts. Even in the same place, there is a range of uncertainty. Droughts, by the way, happen to be one of the most uncertain in terms of climate. But if we don't do this, we don't have any insight. I would take something as opposed to nothing, and which does not mean that we should not go for the simple physics. Definitely we should, and there is an attempt, as you know, in terms of system dynamical models, other models to do that, but which give us one kind of insight. Which give us, for example, X amount of carbon dioxide increase will mean so much temperature change at a global scale and so on, which will not give us the insights, any insight, at the scale at which we want to operate. How much time? Okay. So this is the uncertainty that we have. Now, what I'll do quickly is go over some of the things that, so I was talking about initial conditions, chaos, etc. Well, some of the things, some of the natural variability that I was talking about, there are these 60 to 65 year cycles. They show a lot of interesting variability, of course, when you have initial conditions. Is this chaos as traditionally defined? I don't know. Definitely it's sensitivity to initial conditions. Is it extreme sensitivity? I don't know. I don't think anybody has looked at with the kind of tools that all of you can look at. But these have implications. So in the context of Indian monsoon, there is a cycle. There are all kinds of cycles in the Indian monsoon, but there is a 65 to 75 year cycle which you only see after you do a low-pass filter with, for example, 30-year averaging. And that cycle, for various reasons of physics, corresponds to Atlantic multi-decadal oscillation, which also has 65-year cycle. Which is why at one point we found that the Norwegian model did best in terms of these things. So in the interest of time, what I'll do is I'll quickly go through some of the things I was trying to show you. So in terms of Indian monsoon, some of the things that we found in extremes. We are still at a stage where many of the insights, even from observations, are getting changed. So we found, for example, that there is no general trend, overall trend in Indian monsoon extremes, but there is indeed a trend, and that trend is in the spatial variability of these extremes. And things about spatial correlations, again, I'll be happy to talk about some of the papers. I'm not going into any of the methodological details here. We have looked at different models to understand nonlinear dependence, including, as I was saying, El Nino and hydrology. So the paper was, the methodological paper was in physical review, and then we had a paper in geophysical research. And then we have looked at complex networks to understand dependence, oceanic dependence of oceanic variables and how that influences regional land climate, teleconnections, which is one of the most not so well understood events. And we have done both prediction and explanation based of that. I'll not talk too much about these, but we have also looked at what does that mean then? What do these climate events mean for infrastructure? So here is one example that we did on Indian railway networks. Indian railway, simply because we found data for that. Now we are looking at lifelines of Boston. And also we have been looking at biodiversity and species loss, behavior models, all in this context. We have been working with society. So here is this report that came out for the city of Boston, where our work was on extreme temperatures. This was basically, almost all universities in the greater Boston area who came up with this report. This has just been published by the city of Boston. Right now, our group is working with town of Brookline, Mass. On climate and public health. Here is actually where I wanted a lot of inputs from you in terms of your experience with dealing with epidemics and such. And we also have been working with trying to work in this area of climate risk management and infrastructural resilience through a spin-out which just opened, which we have been working also with market leaders in these areas. Thank you very much. Sorry for the time.
You can take a question.
El Nino.
This connection between El Nino and the monsoon in India, for example, how did people discover that? How do they discover these connections?
Interesting. So historically, fishermen in Peru used to go fishing, and then when they saw that there are these kind of fish or the water is a bit warmer, somehow that relates to I'll get more rainfall or I'll have droughts in Peru. This was there. And then there was somebody called British scientist Walker who sort of found some relations. So this is happening again, so found correlations and things. So this is a phenomena happening here which is leading to this. So there is this interesting anecdotal, precedence which led to this. After that, of course, there is by now, a lot of modeling, data analysis, all kinds of things. We have a fairly good understanding of the basic mechanics of El Nino, which is not to say that we can predict quantitatively exactly, but we have an understanding. So all these things happen. But it started with fishermen in Peru, very interestingly. Yes, now we know the causation. And there is this water level that moves along one way and then another way. So there's a reason for this cycle, but it's not that cycle. So it's quasi-periodic.